Alright, in the last video we developed this algorithm to calculate a convex hull, which is kind of like a way to triangulate some points. So we have to start with a triangle, and then we can construct new triangles like this. And that process sort of goes on until we have wrapped the whole set of points in triangles. So I think now it should be done. Soon. I think now it's done. So now we want to try to apply that to this rapid So if I go here to run and I change it to main, and then let's go to the main file, then you can see here we have this set of points that make up some 3D structure, which happens to look like a rapid. And now let's try to triangulate that. We may run into some scaling issues because before we were working with like 20 points, and now we're working with 35,000 points. So we'll have to see if it can even like run in a reasonable amount of time. So we want to create a mesh eventually. So why don't we, and let me turn off Copilot just for now. Why don't we make a function that returns a mesh, and then it takes a, so let's call it calculate convex hull, and it should take some points, and maybe that is just pointed to some vectors like this, and we also take how many points there are. Now we have to do a couple of things. First we have to find the initial triangle, and we haven't really talked about that. Then we have to run the convex hull algorithm that we developed last time, and then we have to turn the result of that algorithm into a Rayleigh mesh. So to find the initial triangle, I think we can do the following. Select 3 points with the largest y component, or x or z, doesn't matter. Check that they are not on a line. If they are on a line, we cannot make a triangle from them, so that's not very good. If they are, we cannot make a triangle. But otherwise we are good to go. So let's start by finding those. So we can call them, let's call them S for start. So S1, 1, 2, and 3. And then we probably need like a couple of y values here. And actually I think we can do this, and we can set them all equal to the first one, like so. And then we kind of want an invariant that is like this, which is true right now. But let's go ahead and loop through the points. And then we're gonna see if, let's actually just get out the point. So if point y is greater than y1, then we can basically shift things down. So like, it's a little bit redundant that we have both of these, but so let's not do that actually. Let's just do this. And now here it's like, if this is greater than the first starting point, then we can shift things down. 2 becomes 1, and 1 becomes this point. Okay, and otherwise, if it's greater than s2.y, then we don't have to shift quite as much. And otherwise, if it's just greater than s3y, then it's very simple. S3 is equal to the point. So this is a way you can find like the top n, in principle, things just using one loop through the array. So that's quite nice. So now we have the starting point. So let's check whether they are in a line. So we can do it the following way. We can have a vector between s2 and s1, and s3 and s1, and then we can get the dot product between those, and kind of like the cosine of the angle will then be the dot product divided by vector 3 length of d1 times vector 3 length of d2. And then I guess we need an epsilon, so let's do an epsilon, and if the cosine of the angle minus 1 is less than this epsilon, actually we don't really need the absolute value, but let's just keep it. If this is true, then we're just gonna fail. Initial, let's say unable to construct initial triangle. We're just gonna fail, and we can put it to do like handled failure better. For example, try with x or z. And I think we need assert. We do have assert, so that's good. And now we have the initial triangle. So now we need to have this list of triangles. So I think it's a good idea to just copy this stuff from the prototype. And do we have like DA append? We don't, so let's get that as well. And here we go. Now we have DA append. So now we can actually make the initial triangle. That is pretty easy. Do need to do this, I think, because it's a C. But the let's just put them on the same line. The initial triangle is just these 3 points that we found. And then let's instantiate a dynamic array of triangles, and let's put in this initial triangle. All right. The next thing we're going to need is to actually run the algorithm. So if we go ahead and see, zoom out a bit. Not that one, this one. So we kind of need to run something like this that runs the full algorithm down here. So let's go ahead and try that. And here we need a triangle index. That's going to be 0, and we need an edge index, which is also going to be 0. And we run this. Then we need the expand convex hull algorithm function rather. So that's this guy, and that has a couple of helper functions that we also need. Has edge, I think, is existing triangle, add triangle. I think we never actually really used that, but we can anyway see what the compilation errors end up being. Let me remove some of this junk. And now we have that. So I think I want to try to say iteration this, and maybe we can do this, and let's have here iteration so we can kind of keep track of how fast it's going, because I'm worried it might be super slow. Let's write down here. And now we can already try to run it. We won't be able to see anything, but we can just try to run it and see if we can even run it. So here in the PLY data we have a vertex. I think it's better to do just a vector 3. And it has the same field, so I think it should just work. And actually, let's just check there's no inadvertent references. So here it should be vector, keep writing vertex, but here we have some vertices. And now these are the only references. So I think that's good. Let's now do the following. If is key released key R for run. Let's run this function, calculate convex hull, with the PLY data. So data dot dot vertices and data dot number of vertices. And let's go ahead and try to compile it. So that didn't compile because here it wants a dynamic array of points. I think that's not needed. Number of points, we'll say. So let's see where the points are being used. Here they are being used. Number of points, this should be, this one can now just be, use the pointer straight up. Same here. And because we don't remove points, we don't really need it to be a dynamic array anymore. And I think that's okay. This one shouldn't be, it's already a pointer, so it shouldn't be we shouldn't take the address, so let's try to compile it again. This has to be vector 3. This has to be something, what went wrong here? That one too many parentheses. And too few arguments because we need endpoints. And now it's compiled, so let's try to actually run it. Not sure what happened. Didn't seem to print anything. Try again. Pressing R like crazy. It did start to write something. Let me close it and start it up again. I pressed R. So one possible issue is that it's just very, very slow. Okay, here we got some stuff. Could also be it's not flushing, so let's try to just run it from here. We get 15 and it stops. And I wonder why that is. I mean, there's clearly more than 15 triangles. Let's do something like this. Final triangle count is tries.count. So it somehow it only manages to make 4 triangles. Does sound like a bug. It does sound like a bug. So maybe the question is, how many points do I actually get? So let's say starting convex hull calculation for this many points. Let's run it and let's have a look. So it is the correct number of points. But it I'm not sure why that is, but let's try to turn it into a mesh now. Yeah, let's do that. So what do we do here? Kind of copy paste this. And what is the vertex count? That is a good question. Probably we can say the number of triangles times 3, and the triangle count is of course just the number of triangles. Then we should allocate some stuff. This looks correct. And then for each triangle, we are maybe we say times 3 and here plus equals 3. And then we could say mesh vertices I times 3 plus 0 is equal to no, wait a second. This is wrong. It should be mesh dot vertex count. And then this one is supposed to be the x component of the first vertex. So this is a bit confusing. Let me change it around like I don't. So let's loop over each triangle. Okay, that kind of makes some sense. And then we have to set the first vertex. So that's going to be some kind of a vertex index. And then this is the x component. So we go tries, items, this triangle. and the first thing in that, and then x. And that should be z, and this should be a y. And then here we basically increment this, I think. And then here we say, let me also get that thing. And here we replace that with b. And here we replace it with c. So that should basically be it. So then we've created the vertices. Then let's upload the mesh. It's not dynamic. And let's return it. And then here, instead of doing this, we can try to say create convex hull, calculate convex hull. What's the name? Calculate convex hull. Data dot vertices, data dot number of vertices, and let's see how badly that fails. This is probably going to fail. I don't see anything at all. So maybe let's make two meshes. For both of them, and we'll also unload both of them. And that failed. That's interesting. I don't see why it should fail. Okay, now it didn't complain, but this is the triangle it created. Yeah, so that is clearly not correct. So let's try to see what kind of points it finds. Starting convex hull from maybe we'll say only four digits. S1.y, S1.z. And finally 333. Run that, and so this is not correct. I'm pretty sure those numbers are but we do start from here. That's very interesting. So what happened when we read the PLY data? Well, we kind of know that's correct because of the bunny being shown, so it cannot be that. Can it be something with this way of initializing things? what if we write points? So here, maybe just do it like this. And still, it's kind of super crazy. What happens if I press run again? The thing is that these, well, maybe there are points out here. I don't know about that. But I don't think so. And if we remove this, it doesn't change anything, which I wouldn't expect it to, but just wanted to make sure that these functions weren't changing the data in some way. Okay, I think we have a bug. So when we read the PLY data, so I try to check that we don't get invalid values. And you can see here it says failed at this line with this contents, which is this line here. And this is outside the actual coordinate data. Somehow it's reading down there. So that's definitely not correct. So let's try to figure out why that is. Let's break in main. Let's run. Let's open this thing and let's step into it and see what happens. So it's gonna do some stuff here. We can go ahead and, what is line, for example? We can see what that is. Maybe we can line the start. Is it something like this, maybe? No. What is line.length? Okay. I'm not sure how to get it to print exactly what I want, but it doesn't really matter. So let's see that it gets the number of vertices correct. Actually, we kind of already know that. And now we're gonna go ahead and we can try to print contents that start. But maybe do it like this. Okay, so that looks promising. Here we have 003782, 003782. So that seems correct. Let's go over here. And now maybe we can say line start at line length. Okay, that looks fine. Maybe we can even say display line start at line length. Now we chop something, so it should become smaller. It should remove the first number. So it did that. That's great. Now we chop something, it should become smaller. Great. And chop something, should become smaller. Great. And now we chop a line. So what happens to it? it seemed like nothing happened. And is that because when we chop the line here, it's okay, it's on content, so that's actually fine. We go to the next one, and I think I see the problem. We're kind of skipping one. So this is 00680, and this is 086600. So yeah, that's kind of a bug that we don't really need that chop line. So now it should look a bit different if we try to show the model. We should basically have twice as many vertices. I don't know, I guess it is a bit more dense. Not extremely, but yeah. And let's try now to... Okay, now it's taking quite a long time, as you can see. And this is exactly what I was afraid of. But at least it's running now, not just stopping. And there's probably a bunch of triangles. Let's try to quit it. I cannot actually quit it because I disabled the cursor, so it's amazing. What we can do is, I guess it's called main, or what is it called, 3D stuff. Can we even see it? We cannot. Why can I not see it? Maybe because it's running from inside NeoVim. So actually, and even that I cannot, for some reason I can only see it from here. But let's try to kill it like this. And yeah, okay, so that kind of works to kill it. So let's now run it over here instead. It's not main, it's, can I do bash run like this? So I'm afraid this will just slow down a ton. So we need to fix that. But what is causing it? You know, before we go too far, maybe we just try with like a subset of points. Let's go here to the main function. Let's try not with all the points, but let's try with 100 points. And that failed. Let's try with 200. It's quite a bit of running time to do that. So we have to check out what is happening in this expand convex hull function. And this is still going, it's taking way too long. Let's try not with 200 but with 50. It's unable to do that. How about just 10? Somehow it doesn't. 110. How about we skip like 5,000 and then we take 50? Still not. Okay, it's probably not gonna work. On second thought, let's try this. Let's try to 200 because we know it can actually start doing stuff there. And then we can go ahead. I kind of think this is not necessary. Let's try to remove that. And now it was instant, but clearly wrong. So that's great. Love it. But what if we do this? Still instant, but still very wrong. Now we have one big line of something. And how about we, and you can see it's not really running for that many iterations, which is kind of weird as well. Am I missing something? This looks correct. And the final triangle count is 2, which is also very weird. So maybe we do need this, because when we have this, we run for a long time. So what is that one doing again? So here we have to check that those 2 points have not already been used for an edge in another triangle. That makes sense. We could use a hash map for this, so we don't have to loop over all the points. But for now, that is not, seems to not be what's causing the issue. It seems to be this thing that's causing the issue. And why do we even loop here? Like there's some kind of weird bug. Yeah, we shouldn't need, like the J is not used, right? So we should be able to do this. It seems to iterate faster, but still it is too slow. And still, if we remove it, it's just gonna give junk. But probably it will also give junk anyway. Yeah, I do think we do kind of need this. But looping over all the triangles is not gonna work, because maybe let's try to keep track of the triangle count. Triangle count is this. And yes, I turned back on Copilot. So you can see the number of triangles is growing very fast. Well, not very fast, but it's growing. And the time is kind of growing as the square, I guess. So what we need is put this in a hash map. And to do that, I guess we should use like, I think we can do this, and it's the data structure one. Let's try to get that. And this is not the URL. Is it because we need to write like blob master or something like that? At least that gave us a file. So now we can try to remember how this works. And that was also not correct. Okay, give me a second. Right now we should have it. Here we go. So let's do this thing that he says to do here. And then it's like hash map get and stuff. And what were we doing? Expand convex hull. So now I think we need some kind of indices. So something like this. There's probably a better way to do it. Maybe that doesn't work. I think these indices have to be indices into the array of points, otherwise it's going to be weird. I took a bit of a break and now I'm back. So let's try to continue where we left off. And we have these two checks that we need to do. We need to check whether an edge has already been used twice, and we have to check whether when we get to a candidate point, that point is already part of a triangle. Or rather, the 2 points that we're trying to create a new triangle from, and a new point, if that already has a triangle, we don't do anything. So we need kind of two things, and we downloaded this this header-only library, and it has these functions for hash maps. These hash maps, they work with a kind of a special struct that is supposed to look like this. So let's make something like this, and we'll need two of them, I think. So we'll need like an edge key value pair, and we'll need a triangle key value pair. And the value is not so important. And the key here, it needs to be a, let's say, edge key. And let's turn off Copilot. So an edge key is supposed to be 2 integers. It's like edge index 1 and edge index 2. Like that. So that's the edge, and the triangle, I can also just put a boolean here. We don't, actually here we do need a count. No, sorry, it's in this one we need a count, and this one, it doesn't matter. We just need to see if it exists or not, and we'll determine whether it exists just by whether the key is present in the map. So this value doesn't really matter, but so here we have the try key, and the triangle key is three things, three indices, one for each corner. So it will be like this. Now this function should then take some hash maps, and those hash maps, they just have this type. So we'll call this one edge hash map and try hash map. Alright, and then instead of this thing is very bad because it has to, well, it's actually not that bad, but it has to do these calculations, and they have some multiplications and comparisons and things like that, and it might just, so probably this won't speed it up so much, but we'll keep this now, then we can check later. So inside the hash map library there should be something like checking whether it has a key. Okay, so not here, but maybe this one. Or maybe this one. Okay, so this one returns -1 if the key is not present. So edge exists. We kind of want to check for edge. So actually we cannot easily do that because we don't know in which order they are coming in. And here we have these indices. So actually I think we need also some new fields on the triangle struct, because we need to know which indices in the list of points these belong to. So C, A, B. So it's always I1 and I2, and we check whether any of those is present. Actually, let me just do this and this. All right, so what do we want to do now? Let's just implement this one and see how that works, how that is supposed to work. Let's put it up here next to the edge hash maps. So let's do this hash map get index, and I believe it's the hash map first. And oops, and then it is, we need to construct a key from these two values, and then we have to check for that. So basically if this is not -1, it means it's present. So we can return true, the edge exists. And then we can do it again, but with these two flipped, because we don't know the order. And we can call it 2. And if neither of those are present, it means that there is no edge, so we will turn false. And that's about it. Great. So we kind of need to do a similar thing here. We can call it check for try, and it will take the try hash map. It will take these two, and then the potential one, which is I, and then let's implement that. It's very similar to this, except I suppose there's 3 different ways, 6 different ways. So edge becomes try, and here we need to add some types. And this stuff can go away. Here we'll do like this. Why does it say IA? That's a mistake. It should be I1. We can do I1, I3, I2, and let's also do just index here. So it's easier to copy and paste. And I don't really have a good way to check each permutation other than this, so this is just what we are going to go with right now. And we need one more. All right, so we have those two checks. So this should be much faster, especially this one, because it was really looping through all of the existing triangles. So we have those checks, and now when we add a new triangle, we should also put in a new thingy. So it is really called put. So hashmap put, and let's start with this one because it's a bit easier. And we need a try key. That's going to be I1, I2, and this one. And what's the value? The value is just going to be true. Alright, and we also need to put something in the edge. So we need to get the existing value. And I suppose let's do this. So edge hashmap index is hashmap get index edge hashmap of edge key, and the new edge that has a triangle is this. Yes. So if that index is -1, it means that it doesn't exist yet. So that means we can say here new value means the new value is 1. And here the new value is edge hash map index plus 1. And then we need to say edge hash map edge key I1 I2 is new value. So we do have a bit of an issue, which is that if this is equal to -1, then I think we need to retry it, but with the opposite order. So something like this. And that should be that. And it just made me realize there is kind of a mistake in this one, because if it's not equal to 1, it means that an edge has already been made. But that is okay, I think. I'm kind of losing track. Expand convex hull. Yeah, so this is checking for another triangle, and we want to know if it's part of 2 things already. Yeah, so check for edge, and then we have to return if edge hash map index 1 is greater than 1. It's really this we need to return. Same here. And yeah, there we go. Final thing before we can run it is that this, or 2 things actually. So this try DA thing, in the triangle we also need some indices. So we need A index and B and C, and that means in here where we are constructing a new thing to put in, we need to say I1, I2 minimum index, and same here. So the initial triangle, we need to keep track of the indices as well. So here I3 is I2, I2 is I1, and I1 is I3 is I2, 2 is I3 is I. And then we simply put those here as well. And then we need a couple of hash maps. Set up hash maps. And I believe you just declare a pointer. The starting value, well, I guess we will see if that is true. So we need the edge hash map, and we need the triangle hash map. And we can already put in some stuff. So let's say hm put edge hash map. And we're going to put in edge key for I1, I2 is going to be the value 1, and also I2, I3, finally I3 and I1. So this is the initial edges, and let's also now put in the initial triangle, and that just has some Boolean dummy value that we don't really use. And finally, it is the edge hash map first and then the triangle hash map. Let's try and compile it. Right, so here we have to say that value, and check for triangle. It needs that this edge hash map is really a triangle hash map, and this one is near comma. Okay, and this is some kind of macro, so we have to say try key k, just call it k. Probably have to do the same here. Same here. And we've got some semicolons. And this has to be value. And this stuff. So let's get a macro working. So h key k. Start with that. Here we'll make a macro and we'll say forward. That didn't work. So try again. So forward to comma, and that was also wrong. Start over. So visual mode, forward to comma, one back, delete, one up, k equals this, and go back, forward to comma, one, append, k, and down. So let's try that, and that actually works. Can I even do it here? So try key, it's going to be tk, and that didn't work because of reasons. Okay, so it ran and then it segfaulted. So why did it segfault is the question. Let's check that we're using the interface correctly. So these are all like value types, I'm pretty sure. This is how you declare one. So where does this segfault actually occur? Maybe we just try to run it like this. And it is somewhere in there, but it is somewhere in the hash map, but it does run a few iterations, right? And then suddenly it bugs out. So yes, go here, break main, run. Let's see. And let's step into this, and we need to break after this and continue. And now we have to reset to it because we printed some stuff, and I cannot handle that. And same thing here. Yeah, so maybe this is not the best way to do it. Let us see, calculate convex hull. Let me put a breakpoint here, 704. Continue. And continue. Continue, continue. I think this one still works, so that one works. But this is the iteration where it fails. So that's all right. Seems all right so far. What is whole count? It's 4, it's not too bad. And we go in here again. Where's K? Just realized something. That this entire loop is very silly. We'll fix that a little bit in a little bit. Okay, here we have another key. It's all right. Let me put another breakpoint, because I think it might be after. So 598. Okay, so far so good. We have this thing. That seems all right. Put it into the hull. That's fine. That is fine as well. And there is where it broke. So can I... That doesn't look right. Is it... Why does it look like that? Who knows? And what is STBTS header B capacity? Alright, so that doesn't work. All right. I wonder why that is. So that should be all right. And we're just trying to insert a key. And what does this thing return? It returns this. Let's try it again. Now we get the sigfold, and now we can do something like STBDS header. Wait, sorry. How was it? STB array header. We do a cast. Of B, whatever B is right now, -1. That's a null pointer. So if I say now capacity, it should also say, So that's very weird. Let's try to see what happens here when it's initialized. So 691. And Now it's obviously a null pointer, and if I say stp ds array header, cast it to a pointer to that, I think this is how you should do it. That's something random, but let's now try the same thing. Now if we print this, it shouldn't be a null pointer anymore. It's to be ds array header, like this. It's also something. It's array header. And what is the capacity? Capacity is 0. But I just put something in there. Maybe it just means that there's no leftover capacity. Do we have count? It's not count, it's length. That also seems very wrong. I wonder if we need to say that it's size t. Didn't work. Still not. That's very weird. What if I just print this? Dereference. Yeah, something is very off. Maybe I just don't know how this is supposed to be used. stb header. It's very strange. Maybe the thing you use it with is not the hash map itself. It's the only thing I can think of. So it has like, what was it? stb ds header b capacity. Okay, so B is some thing. Like that, okay. Okay. Try this. Still nonsensical, so that was not how you use it. Maybe I shouldn't spend too much time on this. So what could it be? What could it be? Are we using it wrong somehow? I don't think so. This is supposed to be a try key, right? Because up here we defined to have a try key. The value is a boolean. Okay, let's try to run it again and let's go to 609. So first of all, let me just make sure it's compiled, and then we run it and we break 609. We run it, and I think we can continue it a couple of times. So now maybe. So print K, nothing weird there. And what if we cast it to a stbd ds array header? That just seems wrong, and yeah, that ain't it. And then it's false. Okay, so maybe we can do this, and we can try to step into it. I don't know if we can even do that. Okay, so here we go. We have A, it's not null. Kind of shifted the pointer a bit, which is interesting. Where's the table? Who knows? So it tries to call this function and then it breaks. And this is some obscene number, which I still don't think that's correct. Okay, anyway, maybe we also add a breakpoint in here. Shit, I think I forgot. It's be DS H 795, I think it was. Is that even? Okay, somehow I zoomed out. Whatever. Okay, 795 and almost correct. So 764 is probably what we want. 764. Okay, and we're already in there now. which makes sense. Okay, let's continue, and we're here again. And it's probably let's continue a few times. All right, I think we are there now. Why is the minimum length that large? Yeah, it's for some reason it's setting the minimum length and capacity to be a huge number, and that's probably making the reallocation fail. So if we went here and said like assert b is not equal to null, I think that one will just fail. Let's try to compile it, and you can see that that one fails now. So for some reason it's like corrupting. And I think can it be because when we do this stuff, those pointers, they get reallocated, and that means they get modified, but then they only get modified inside this scope, and that is causing issues. So just to test that, let's put them out here. Okay. And I guess, can we even do this? Is that a thing? So now we have those out there, and then in here we don't need to do that, and they don't need to be passed here anymore. Okay, it didn't crash. So I think that was actually the case. And you can see it's much faster now than before. It's still a slow algorithm. But at least it's running at kind of like a constant pace right now. And let's actually fix... I shouldn't have run it in here. That was a mistake. So let's kill 4827 and do that and expand convex hull. This stuff we don't need. It can be outside the loop. We don't need to have it in the loop rather. So, and then let's comment this out. This one is all right. So can we, how is it time works? Not this one. How do you get Is it like that? Yeah, so we can say include time .h, and then we can go to main, and we can try to time how long this takes. So we have time t0 is time null, and then we have t1, and then we can say clearing the convex hull took this long, and then let me go into calculate convex hull, and let's get rid of some of these debug statements because they are not so interesting. And finally expand convex hull. All right. So that was pretty kind of a gotcha that you cannot pass these as arguments. I wonder what the idea is, like how you're supposed to use them. Okay, but anyway, let's go here. Let's try to run it, and then I will see you once it's done. All right, so I think it's taking way too long. You can see here I added some logging now, and it's well, that was so it has calculated like 8,000 triangles, which sounds nice, but then if you look at the actual data, probably will need to get 70,000 triangles calculated. So that's a long way. We need you can see it's doing like on the order of 10, 30, 20, 30 triangles per second or something like that. So it's too slow. We need like a factor of 100 probably. So I'm not sure exactly how to do that. So because of that, we're going to make a small test where it's reading the PLY data, and here, where is it? Here we find the number of vertices. So I'm just gonna manually say that maybe that's 500 instead. Let's try to see if that actually runs in a reasonable amount of time. Still is creating a lot of triangles. That's very surprising. So let's cancel it once again, and let's go here and say here, if this is greater than 2000, we can break, and then we'll see how it looks. Okay, so clearly it's very wrong, and that's very surprising. So we kind of do have a rough outline of the rabbit, so that should be all right. Wondering if this could be the problem. No, it's not about initializing the data. We upload the mesh, that looks fine. Could there be something here? What if we break at 726? We run it, takes a bit of time, and then here. Right, so tries items I, let's actually display that. And those numbers look all right. So let's break here and let's say continue. Still looks fine. Continue. don't see any issue there. So let's do something like assert vector 3 length of tries items items IA is less than 2. It's probably alright. We'll do that here and here as well. Except that will be B and that will be C. And now I kind of expect it to fail. But it didn't fail. But the triangles are all messed up anyway. And this is a big problem. It should just be the vertex count, of course. Let's try to run it again. And now don't see anything. So maybe let's try to assert that vertex index plus 2 is less than mesh.vertex count. Right, so that's why we need times 3, because it's floats. Okay, so that was actually correct. That was actually correct. And these are the lowercase. Alright. What if we don't draw the first one? Then we just get this horrible thing. So we know all of these vectors are kind of reasonable values. And this draw model is given a position. So how about we move it down a little bit? We'll see what happens then. These points are also weird. Why are they there? Let's not draw this and let's see. So we do have some random points there, but maybe that's correct. Alright, let me debug a bit off screen. Okay, I think I just realized the bug. Here we shouldn't add a 1, we should add 3 actually. So we add 3, and we add 3. Let's run it. And it looks less crazy, but still it's obviously wrong. Do we have some kind of silly mistake? Vertices, X, Y, Z, 3 components per vertex. Alright, I think I found a bug, which was that sometimes we would make, where was it? It was in here. Sometimes we would make a very flat triangle, so now I'm checking at this point that we're at now, checking the candidate point is not in the triangle already. And if we now run it, there's still a bug, but you can see it's creating a lot of triangles, probably way too many, and I think I have an idea why. But now it's at least looking approximately correct. You can see it is kind of wrapping these points. But if we take a look at, for example, this region, I think I saw an example. So for example, here, so here in the middle, I think you might be able to see. All right, sorry, some dogs barking, which makes my dog bark. But you may be able to see that from some of these triangles there are extra lines coming out, which I'm pretty sure shouldn't be there. So I think there might be an issue with the edge check here. So let's try to double check that. And I wonder what would happen if we do this, just for fun. Just for fun, and let's also just double check that this is all right. And here we could assert that the new value is equal to 2. But let's not do that right now. Okay, so now it didn't do anything, and that's because the first triangle, it all of its edges are of course part of a triangle already, so it will just stop. So that makes sense. What if we do this, and we do this just for a check? Still it's running. So that seems to indicate that we're not creating extra edges where there shouldn't be. But I still think, what if we, maybe it will make it easier to see what's going wrong if we only draw the wires. Yeah, that is way too many. Way too many. It's like it's connecting everything to everything. So could that be the edge check? I don't know, but let's try to revert it to the old one. And that failed. Let's print the new value and then assert. And then for some reason this edge check actually doesn't work. Which is very surprising to me. AB, BC, CA. And that seems correct as well. Maybe is very bizarre. If we do this one again, and then we had the 50,000. Let's just do like 10,000, so it's a bit faster. Maybe that will show the bug as well. So it does seem like it's showing the bug. And that is also kind of too hard, so read pure white file. We had this hard-coded limit. Let's try it with just 100. And that doesn't work. Let's try 200. All right. All right, all right. It's hard to see, but it does look like some of these lines are going into the interior of the... It's actually impossible to see. What if we try to not do this and then we run it? That is way, way, way slower. That's interesting. Which means that this loop is now the bottleneck. Which makes sense. I guess it's not nice that we have to check every single point. So maybe instead of 200, let's try 2000. That failed, that's interesting. 1000. Maybe it is correct, maybe it just looks so weird because the mesh is not fully formed. What if we try to get all the vertices, but actually let's do this, and let's say it's we subsample by a factor of 100. It's still gonna be too many actually. Let's say 300. And then here we only read every 300 vertices. Let's try that. And that didn't work. Maybe if I skip a few. Okay, so that's a bit annoying. What if we, instead of Y, we just check on Z? Instead of Z, we check on X. And none of that worked, so let's go back to Y. Apparently, let's try just get something running, please. What if we remove this? Just try to be stupid. So that didn't, well, we can remove it and then we can say, let's subsample this. You know what? This doesn't work. I think it's the issue. Yeah, we don't really want to do it here. So let's go to the main function. So we read, this is the full data, but then when we create the mesh, maybe we want to say like subsample factor is 300. So then we divide by that. Divide by that. That one is probably okay. And then here we can say plus equal subsample factor. And I think that might work. Let's try that. And 287. Maybe we'll just do this for now. It's still calculating. And it's still very slow. It's probably because I forgot that it doesn't really make sense to do it. Well, we kind of want to do it there too. And then here as well. Maybe let's not do it. I take it back. Let's not do it here. Alright, so PLY data. Let's make a new one. Just call it data. We'll say subsample the raw data by a factor of 300. This can be the raw data. And PLY data, subsample, and that is not what I want. In vertices is going to be this divided by n, and let's see if Copilot can do that, because I'm like, that seems correct. Let's try that. And that failed for the same reason as before. But if we say 1, that should just work, right? And that does do it. What if we subsample by 1000? And maybe just let me just see what the hell is going on. So if we subsample by 1000, we get that. What if we subsample by 300? What do we get then? We get this, and it looks fine. I don't see why it should fail. It's even like a bit too much. About 100. Yeah, it looks good. Let's try to calculate the convex hull. And it fails. we're gonna print 3 points. Using Copilot. That's interesting. And what is actually the... So how is that actually failing? What? Okay, turns out that apps is for integers. So that's great. And we have some here as well, and that's probably also wrong. So let's go ahead and go over the full file and say, let's replace it. And let's check, not that one, we did that one. No, yes, 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 no, okay. Now, if we run it, so we can calculate the convex hull now. We can probably even draw it. There it was, sorry. And it even looks correct. I want to do something. I want to say draw convex hull, yes. And then we say if draw convex hull, we do these two things. And if is key released, maybe it's gonna be key for B for draw. We're gonna toggle that. Let's do this, and we're going, and so it is actually the and it's a better idea to use D, I just realized. So let's C for convex. So this is actually a convex hull. It doesn't look like the rabbit, but that's because the rabbit is not a convex structure, which is something I didn't think about when we started this. Let's try to subsample it a bit less. Factor of 10, see if we can get that working. It is very, very slow. But here we go. So you can see we have a very dense rabbit. We can draw the convex hull, and it obviously fails because it's not covering. Well, that's because probably we stop too soon. So I think this might be okay. Yeah, I think that's gonna do it for this video. There's still some work to be done. I'm gonna think about what we can do. So, until next time, bye bye.